In this video, I'm going to demonstrate an example of a multiple regression approach to a typical research question. And the research question here aims to examine the relationship between life expectancy, education, income level, and murder rate. And in this screenshot here you see an Excel sheet that has just a clip of this Excel sheet listed for a number of states in the United States. So here we have 50 states. You don't see all 50 here on this screenshot, but as you go down, there are more rows here, and the individual state represents one of the cases in this examination, where we have life expectancy in years, the percent of that population that graduates high school, the estimated monthly income, and a per capita murder rate for each state. So we have a sample size in this particular case of 50. So we have, once again, Y is life expectancy in years. The first predictor variable, or X1, is education, so the percent of adults that have a high school diploma. X2 is the dollars per person per month. This is an average in the state, and again, these are for adults. And then X3 is the murder rate per capita, or converted to per 100,000 people. So one can take a correlation approach to it, and when taking a multiple regression examination of a study like this, one would have to define which variable is the outcome or criterion variable and which variables are the predictor variables. If you just conduct a straight correlation analysis, you would not need to do that, and I'll demonstrate, and we'll take a look at the correlation matrix on the next slide. But with a regression approach, we're always trying to examine the value of certain variables in predicting the outcome. So the outcome variable should first be examined. And even with a multiple regression approach, it's recommended that a correlation analysis first be conducted. This is the calculation of Pearson correlation coefficients across all of the variables. So in this approach, you're not necessarily setting up the predictor variables and the outcome variables. You can still have that in mind, but the correlation approach is going to throw all of this into one analysis and repeatedly compute coefficients and present that in a correlation matrix as we see here. So if we take a look at life expectancy, once again, we keep that in the back of our mind, and we examine the individual relationships between high school graduation, life expectancy, income level, life expectancy, and the murder rate of that state and life expectancy. It's also important to examine the correlation coefficients between the other variables that would eventually be our predictor variables. These would be also important to document. On the next table below are the t-values computed for each of the correlation coefficients. So once again, because we're talking about Pearson coefficients, these are bivariate. So it's only the correlation between life expectancy and high school graduation at 0.5822, life expectancy and income 0.34, so on and so forth. And each of these Pearson coefficients will have an associated t-statistic, and that gives us a sense of that level of statistical significance. And the bottom table here are the calculated p-values, so the probability that we would be committing a type 1 error in rejecting the null hypothesis that the coefficient is actually 0. So for example, as a review, if we take a look at the correlation between life expectancy and high school graduation, we see that there's a positive correlation of 0.58, and because this is a social science type of study, we would rate this correlation strength to be moderately high. So we see that we would state that because the p-value is very, very small here, so this is 9.1961 times 10 raised to the power of negative 6. That's what this indicates here. This is a really small p-value. So is there a risk that the actual correlation is actually zero or non-significant? So you might look at this and say, well, that's absurd because it's 0.58, but there's always a statistical chance that we could be making a mistake, and that's what the type 1 error is. So you see that all these correlation coefficients, with the exception of the negative 0.23, the negative 0.23 has a p-value of 0.10797, suggesting that this one does not reach that level of statistical significance, but that depends on the researcher's establishment of the alpha level initially. And usually it's set at 0.05, but here we see that it's greater than 0.05. So we would conclude that although we observe this correlation coefficient, we would state that it's not statistically significant, whereas the rest of the coefficients meets that standard. So once this is done, then we move on to the multiple regression analysis. And one of the standard approaches, or one of the outcomes of a multiple regression analysis, especially conducted with a computer program, usually is the ANOVA table. And the ANOVA table evaluates the relative weighting, if you will, of the contributions to the total variability in the data. Are the data explained mostly by the theoretical model, as we can see here, or is it mostly explained by the variability, the natural variability in the observed data? So the residual represents, once again, that difference between the actual observed data in the data set and the predicted value by the model. If the residual value is relatively small compared to the model, then our model will have very high predictive power. And how can the ANOVA table indicate that? It's indicated by the variance terms. So remember, the sum of squares is what is calculated first, and then that's corrected by the degrees of freedom associated with each of the sources of variation. So we see that the variance due to the model value of 19.54 far exceeds the variance due to the residual, or the error term, that difference between the actual data and the predicted value of 0.65. So that gives us an overall F value by dividing the model variance by the residual variance, gives us an F value of 30.30. And as a rule of thumb, a critical F value is usually in the range of 2.0 to 3.0, maybe even as high as 4.0 with small sample sizes. But with a value of 30.30, we see that this is going to be very statistically significant. So the calculated p-value of this is going to be far below 0.05. So some of the other regression statistics that are generated from a computer program when examining this is what's called a multiple correlation coefficient. And so with these data, I already ran it through a computer program, and we have a multiple R of 0.815, indicating a strong correlation between the variables in the study. And the R squared value of 0.664 tells us that 66.4% of the variability, of the total variability in the data, is explained by the theoretical model. The remainder, the balance of 66.4% to 100, is explained by the residual error. What the multiple correlation coefficient will also print out is what's called an adjusted R-squared. So this is the R-squared based upon the actual data in the data file, but the R-squared that is adjusted to the population, called the adjusted R-squared, is always going to be a lower value because the data from the sample is considered to be biased against the population. And so the adjusted R-squared is a calculation where the data R-squared is adjusted down for the population. And it's always going to be that lesser value. For these data, the standard error was determined to be 0.803. And that's the variability or the error, and this is a plus minus of the prediction, and this is in units of the outcome variable. The outcome variable, as a reminder, is life expectancy in years. So if we use our model to try to predict life expectancy from those three variables, we would get one value, but we have to consider that that one value is plus minus 0.803 years. So there's actually a range of our prediction. The regression table is the second table produced by a by a multiple regression analysis. And so what you do not see here is the outcome variable, which is life expectancy, because these are the coefficients associated with the model. So we have the intercept value. The first column are the actual coefficients that one would put into the model of the equation, and you'll see that shortly at the bottom of the slide. What comes with that, with each coefficient, is the standard error associated with each of these coefficients. Some are observable here, quite relatively large. Some are very, very small. And we have associated t-statistics. And the t-statistic evaluates if the coefficient for each of these has a statistical value that differs from 0. So it is either statistically significant or it's not. So in terms of the intercept, this is the coefficient that is the y variable or the y value when all the x variables go to 0. And we would have an age coefficient of 70.14 years, plus minus 1.096 if all the x variables were set to 0. Now you note that 70 is much larger than 0, so this gives us a very large t-statistic and a very small p-value. So we would state that this intercept is a statistically significant coefficient. That's not the case with some of these other coefficients. So we see that high school graduation has a very low coefficient value that's not very different from 0. The same thing with income, but not so with murder rate. So as we take a look at the t-statistic, here we see a t-statistic of 1.924 for the high school graduation predictor variable, and it has a p-value of 0.06. Now, if you set the p-value to 0.05, then you cannot reject the null hypothesis. Although it's very close, you would not reject the null hypothesis. And so you would conclude that the high school graduation coefficient is not statistically different from 0. Likewise, with income, the coefficient is a very, very small value, 9.5 times 10 to the negative 5. So you would move this decimal leftward 8 times, 8 spaces, and you can see that the p-value is relatively large. So as a standard, we're always looking for the 0.05. The murder rate coefficient, as we can see here, is statistically significant as a predictor at negative 6.664. That's the actual t-statistic with a very, very small p-value. So this is the second table that is produced from a computer program running multiple regression analysis. And so if we start with our prediction equation, if we state that it's our prediction equation, then we're going to lead with y hat. Y hat indicates the predicted value from the computed from the actual data, where we have B1, B2, B3 associated with each of the three predictor variables, and these are the individual slopes associated with each of those predictor variables. Now, taking the coefficients and substituting those coefficients into our prediction equation, we would have an equation that looks like this. So one could use this and input different variables or different values for x and come up with a predicted value for life expectancy. And the residual term, the residual error of 0.803, that was the last bullet item on slide number 8, would give us a sense of that variability around our single point estimate here of our calculated life expectancy prediction, not the actual value from the data. So this ends our second video on multiple regression analysis.